Hey everybody, welcome back to Networks. Now I was going to do another Red vs. Blue challenge today, but we had a pretty major storm up here in Northeast Ohio, and I think a lot of people probably are either on their mobile internet or just not going to make it at all. So I didn't think it'd be a great idea to start that off today. If we have pretty much everybody in attendance, I will probably change my mind, but at the moment it looks like most people are going to be watching this asynchronously, and this is not a good time for in-class activities, so I'm going to put that off till later. Actually, the plan was to do it last week, but again, I had VM promises dangled before my eyes and ripped away from me at the last moment, so we're going to probably do it the same way we've done the other different things that we've done through the VM. Um, but I was hoping we'd have a better way. Anyway, sorry about that change, and sorry that the cheating homework was due on such a strict deadline with no follow-up, even though I said there'd be a follow-up because issues, storms, IT problems, etc. Maybe we'll even put that off, the Red vs. Blue challenge, until after the break. So you have one homework that is due before the break, and obviously you're not going to have anything to do over the break because I'm not a horrible person that gives homework during the break. But the homework that is due is something that we haven't really discussed, and that is by design because I don't think that discussing cryptography is all that productive. A lot of you probably tuned out for TLS and all the other different kinds of encryption. But let me mention it briefly, so we'll have talked about it at least a little. RSA is an asymmetric encryption algorithm. There is a public key and a private key. Typically speaking, you encrypt something that is destined for somebody else with their public key, and then they decrypt it with their private key. There are lots of applications. Typically, you will talk to somebody else and you will encrypt something with their public key, and they will encrypt something with your public key, and that is how you two communicate with one another. RSA needs the keys to be generated somehow. It's not just passwords that you type. So it requires a key tool. I'm asking you to write the key tool as well. It's really straightforward in Java. Java can just generate those keys with like 20 lines of code. Now, the typical application, once you've got everything working, is that all the different clients that install your application or run your application, they all get a copy of public key dot whatever. They all get a copy of that public key file, and they access it in order to encrypt whatever they're going to do. If you connect to somebody new, so if you're connecting to a new server or a new client, you want to talk to them, they'll share their public key with you, and you'll save it to your file system as a file probably, and then you'll do something along with that. So that's how it works on the client's end. On the server's end, they save the private key and they never share it with anybody. So you will have probably both on your machine, right? Because you're testing both ends of this. But I just want you to keep in mind that in normal practice, you would only have access to one of those keys, or as the client, you have somebody else's public key that you're talking to, and then your own private key if you're decrypting the messages they send to you. And there's this extra step that's normally involved where you have to exchange public keys that we don't have to do because we're assuming that you've just copied the key file into the appropriate folder, that keys folder that I ask you to make. And then from that point on, communication happens. I'm asking you to do 2048-bit RSA, partly because a lot of the examples you find online are for smaller security strength, and just thought it'd be a minor change to make because it's pretty straightforward to find a lot of great examples of how to implement RSA in Java online. It's definitely the intended way to finish this assignment. I don't want you to have to pound it out from scratch. It's very difficult. It has a lot of weird steps that you have to go through in order to set up the keys and the padding and everything. So I don't expect you to make it completely from scratch. You could make it from the documentation, but even the documentation's not that great. Now, one of the downsides to RSA is compared to other encryption algorithms, it's considered relatively expensive. So the encryption and the decryption are both fairly costly in terms of performance. So what a lot of different applications will do is they will instead set up a TLS session, as we discussed, but that's not an option for us because we don't want to go through the trouble of having to generate a signed certificate. Even though Let's Encrypt makes it free, I would argue they do not make it easy. It is still a pretty challenging thing to do in terms of just the amount of ridiculous IT hoops you have to jump through in order to get your certificate on the system, transmitting properly, etc. So we might do it before the end of semester if we can get a VM with some unblocked ports. Otherwise, we're just not going to do it. But back to RSA, it is relatively performance expensive. So sometimes if you can't do a TLS session, you'll do RSA to exchange some key information. And then you'll do something like AES after that, which is usually cheaper or supported by the hardware on your device. So you'll just exchange the keys to AES over RSA and then go AES the rest of the way. Now, expensive doesn't really mean unusable, so for your purposes it's perfectly fine. And if you're ever designing an application and it doesn't exchange too much info, I would not hesitate to use RSA because the performance hit compared to anything else is negligible. Now, could somebody tell me why we don't just use a symmetric algorithm like AES, which is really simple? You could just have the password or the thing used to generate the key, at least. Just at the top of your program, it could be like public key int or public int key equals, and then we just put a bunch of stuff, usually string, public string key equals, and then a bunch of crap, and it'd be at the top of our program, and it'd be super easy. Why don't we just do that instead of doing complicated RSA where we have to generate public keys with a special tool and then put them in the file and then access them? Why don't we just use good old AES and have the same key on the client and the server end? I mean, for one thing, there's no way to exchange them safely. You would have to exchange them in the clear, but that's not a problem in our case, right? Because we've pre-exchanged them on both ends. Both ends already have the keys in advance. Someone says, because the sender and the receiver use the same key, an attacker only has to compromise the sender. And that's right. But how easy is it to compromise the sender in Java? What do you have to do in order to read that key? Let's say that you packaged your program as a jar, or you managed to pack it as an executable, and then you send it to your different clients. It's running on their system. How do they extract the key from your program in Java? Well, it's trivial, actually, because Java is one of those languages where, given a compiled file, you can very easily regenerate the source code. So that's just one of the features of Java with the JVM and all of its other glory, is that you can always restore the source code complete with all of your variables and their contents, which means that key is really, really trivially readable. And so you never want to put your keys into your application like that. Basically, if you're using AES in your application, be aware that it is likely, at least for the client, very easy for them to extract the key. So if you're going to use AES, make sure everybody gets a different key, and make sure it's not a problem that the client can decrypt all of their own messages whenever they'd like, including the communications back from the server. Okay, that in mind, any other questions on RSA or AES or anything, feel free to post them in either chat. But with that in mind, we are going to start on the application layer, which is the last layer that we're going to cover, and it is the point of all the previous layers. But, spoiler, we've already been doing the application layer for weeks now. So far, we have the ability for one machine to communicate with another one that's far away, and we have all this different stuff that's been guaranteed. We have both physical and network addressing, so networking on the local area network, as well as networking on the internet in general. We have routing and forwarding of traffic to its destination. We've got tons of different multiplexing happening. We've got NAT for routers to be able to support different machines running on the same IPv4 address. And then we've got ports for multiple applications to run on the same machine. all that wonderful stuff. We've got guarantees of reliability in terms of your packets getting there in one piece and getting there in order and all of that stuff. We've got eventual delivery and things like TCP, not necessarily in other algorithms, but at least we have one system where we can use where we get a guarantee of eventual delivery, as well as congestion control. If we do something like TLS or IPsec, which we haven't done yet, then we also have a guarantee of security. So overall, we've got a lot of guarantees already up to this point. And those previous layers basically give us all the needed infrastructure in order to send messages to one another. So I've used analogies to mail a lot. At this point, we have the entire mail service complete, and now we are just worrying about the contents of letters, so what's inside of them. At this point, we have everything in order to get those letters to their destinations done, and so now we just have to worry about how the programs communicate with each other. Now you've already written application code, like I said. So you've written TCP or UDP traffic that carries a specific payload. You've even written your own custom headers. So when you've sent traffic like A, D, 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 Y, D, 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 I think we did AX or something. Or we skipped the Y, yeah. We just did A, D, 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 and then D, D, D for the next integer. We did like A, X, 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 and then Y, Y, Y. So that payload is the application layer, and you even made your own custom header. The first letter of any message that you send designates the kind of payload that it is. Is it an add point, change size, or change color? So you have a custom header. It's 1 character long, a character typically expressed as a byte. So you've got your own basically application code with its own 1 byte header for the type of payload that it carries. You could have made your header smaller. You could have expressed it in terms of 2 bits even, because there are only 3 options. We only need 0 through 4. But the way we've done it, I think, is pretty decent. There's not a ton of overhead in 1 character, so no big deal there. Okay, and there are many other protocols at the application layer. Obviously, there are many popular applications, and many of them rely on a few common protocols. And we're going to study some of those most popular ones to give you an idea of how to use them yourself, because again, they're very popular. The vast majority of applications that don't just use straight TCP or UDP, which is actually fairly rare, by the way, will use one of these protocols. So before I move on from that, let me say again, it is fairly rare for developers to write their application in straight TCP or UDP, which might make you a tad bit upset because you're like, I spent all this time learning TCP and UDP, what the heck? Well, it's the better way to do it, and it's the harder way to do it. And as you've noticed so far, it's not that hard really. So it is a little bit strange, but most developers out there will kind of shy away from writing their code in straight TCP or UDP. It's really not that big a deal. So in some instances, it can become very difficult, but usually the performance improvement over using a existing application layer protocol is substantial when it's possible. So if you have the option, I'd say try to write it in TCP, pure TCP or UDP, until you have a compelling reason to do otherwise. Just a recommendation from me. But in many cases, the application layer protocol is the easier choice because what you're communicating with already supports it, and you don't want to have to write your own basically code to re-emulate that application layer. That's always a possibility. So it's not like you should always use TCP or UDP, just consider it as an option as you go into your career if you ever have any networking code you need to do. Another problem with using straight TCP or UDP is that many platforms are becoming so locked down that they don't even let developers do this, which is surprisingly irritating. Platforms like Android and different mobile and other secure applications or secure platforms, or at least walled off platforms, have sort of a thing against you sending at least unencrypted TCP or UDP traffic straight up at this point, which is definitely irritating. All right, and we're going to be covering these different protocols Hopefully you'll be able to use these yourself at some point, or at least understand how they work, so that when you develop your own application layer protocols, you have some good ideas on how to make them, based on all the great decisions they made in the 1970s. The first one we're going to look at, the most important application layer protocol that there is, without a doubt, is HTTP, the Hypertext Transfer Protocol. It is the backbone of the internet. It is synonymous with internet or web. If somebody says web server, they really mean HTTP server, but no one's going to correct you because they are totally synonyms. HTTP serves the vast majority of requests for data over a web browser, over the internet. HTTP carries text, images, ads, dank memes. It typically does not carry video and voice data. That typically comes in over a separate connection. However, that is also changing. The ability for HTTP to get used for everything has become greater and greater. Now, HTTP historically is designed to only transmit basically text and small format web pages, maybe images, and pretty much nothing else. So the fact that HTTP does all of this is sad in a way, because HTTP was not meant to do all of this, and also great in a way because we've managed to piggyback all of this stuff on top of a algorithm, a protocol that even in its name you can tell was designed to transfer primarily text. So just going back to the lesson of everything is just a stream of bytes, even text is just a stream of bytes, and HTTP can be used to transmit any stream of bytes, even if it's not necessarily text. As the internet grows more and more modern, HTTP shows its age more and more, but it is unlikely to really ever be replaced. So the basics are that it runs on top of TCP. Obviously, we need those guarantees of reliability to do most of the things we do on the web. So we still have to do the TCP handshake and everything when we establish an HTTP session. Keep that in mind. Now, it can run on top of TLS as well if your website uses HTTPS, which is now something like 3/4 of the internet is now running on HTTPS. Again, with Let's Encrypt making it free, and lots of the tutorials out there, and all of the hosting migrating to web services like Amazon and Cloudflare and Azure. Most of the web hosting going to the cloud means that the cloud platforms deal with the certificates for you, and setting up TLS is much easier than when you had to do it on your own home-hosted server. This is really unfortunate for somebody like me who remembers the old internet where everybody could host their own website, but at the same time it is nice to see that almost all of the internet is using secure connections for even not necessarily financial or important information, just using secure connections for everything because it's better for all of us. So TLS or TCP, again TLS runs on top of TCP. It is the secure version of TCP. It's that transport layer security that runs directly above it, and it has its own very long handshake. Remember that as well. So if you're using HTTPS, you have to go through that very long TLS handshake in order to talk to the website you're trying to talk to. And this is also why you will occasionally get something like a certificate error in your browser. Those come up whenever there's a certificate problem in the TLS session. So now you know that whenever your browser tells you that there's a certificate error, it means it couldn't verify the certificate that it got in the TLS session. The reliability guarantees of TCP are used, and HTTP messages are basically just packed into that payload, sent into a normal TCP socket. So from your end, your machine establishes a regular TCP socket, and then HTTP messages come in, and they are passed to an application. We'll discuss which application soon. Uses port 80. I've mentioned port 80 quite a few times. Port 80 is the HTTP port. It needs to be a specific port because when you visit a website, there is no way for it to communicate to you easily what port it's going to be using, so we've all basically just agreed to use 80. You'll occasionally also see 8080 or 8000 as fallbacks. That is not very common, but I guess it's growing a little bit more common. If you visit a website and they're not using the standard port, you're not going to be able to talk to them. So you must be using port 80 in order to speak with them. Stateless. It means it serves clients individually, and it doesn't remember the previous requests that it's gotten, typically from a web server. But what is a web page really? So you've had a web design class, so you know roughly what a web page is. HTTP is used to fetch the content of web pages. Now in the past, and what you probably learned in your web design class, is that a web page was typically based on HTML, so it's a big hypertext markup language file. But these days, the hypertext markup language file mostly just points to a bunch of JavaScript that you have to load, which is unfortunate. We do still see a lot of web pages that use plain HTML, or even static web pages that don't have any dynamic content and just send you the HTML and CSS data and render to the screen very easily. But the vast majority of pages also have to run some script, some JavaScript. So most of the internet is a little bit different today. You still have to load that HTML first. The HTML describes the format of the page and then what resources are needed. Those might be images, those might be the scripts that we just talked about, etc. And then all of those things will be fetched. They are fetched using their URLs, so they are all linked via URL, yourwebsite.org / and then whatever the resource name is. And then those are all fetched, brought together, and the web page is rendered. So a web page is really just a collection of files with HTML as its sort of governor of the layout and everything. So in the traditional HTTP server-client relationship, the server is a particular kind of system, typically either a Windows or an Apache web server. Most of the internet runs on Apache Linux. It is probably something like 70-80% plus. I don't know the exact numbers, but it is vast majority Linux. I would say if anything, Windows has gained a little ground because since 2016, Windows Server has become slightly less terrible and slightly less of a headache. But it's still expensive, which is why most people tend to use Apache Linux, which is free. The cheapest reasonable license for Windows Server is like, I don't know, like $250 or something. And a data center license is like $5,000, which as students, by the way, you can get for free, I think, through Microsoft's, whatever they call it now, formerly known as DreamSpark program. They give students access to different operating systems to play with for free. I believe one of those is Windows Data Center, which is, again, retail value something like $5,000. But it is not something you can sell on eBay because it's only for enterprise customers. So if you were thinking of that, don't bother. No one will buy it. On Windows, if you are trying to run a web service, you will run the Internet Information Services Platform, commonly known as IIS. So pretty much anyone who's worked in IT will be familiar with IIS. IIS is really straightforward. You just install it as a component, I guess you can call it. You install it as a component of your server platform. Then you put all of the stuff that you want for your website into a folder called www.root, and off you go. That's it, pretty much. Anyone can then connect to your IP address and extract all of the stuff in your www.root as you would like. So that's how it runs on the server's end. That's what the application looks like on the server's end. Now on the client's end, the application is very simply your web browser, your Firefox, your Chrome, etc. And of course, web browsers connect to servers who are running IIS or the Apache Linux equivalent, and then they get the files from them. So the server is basically just hosting a bunch of files in some folder, and clients are accessing them according to some set of rules. So at its core, HTTP is really just a very simple file exchanging protocol, which you've already written to an extent. You've been able to send data back and forth in your applications. A little bit more complexity on top of that, and you can send files, and then you're most of the way to HTTP. The thing is that HTTP also has a lot of different convenience features that we're going to look at in a bit. So clients request files, render them, and then occasionally clients have to talk back to the server. HTTP really wasn't super well designed for talking back to the server. So occasionally the client will send a small amount of data back to the server, in text form, which is basically all HTTP supports is sending you back some data in text form. So let's say you click on a link to catforums.com. You want to go visit catforums.com to talk about your cat. What's going to happen? The browser will establish a connection to the catforums.com server via HTTP. So it'll establish a TCP socket on port 80 and then start doing everything that it needs to do to communicate over HTTP. The server will transmit the .html document and any other needed links, any other needed files via HTTP. The first file that the web server is going to get is called index.html by convention. So hopefully you learned this in the web class. In order for your website to be accessible, you've got to have an index.html that the clients will then read and then see where everything else is at. And then from that point on, if you click other links in catforums.com, they might take you to other pages like /dogs.html or /fuzzycats.html or whatever. Those might be other web pages. But the front page, the first page, is index.html by convention. And in that file are all the other resources that are needed in order to load the first page of the website and then show you where the links are to the other pages. Your browser puts all the information that it gets together and renders it to the screen so that you can see catforums.com. So, is it a single TCP session or many? If a server has multiple files, let's say there are like 5 images on top of the index.html file that are part of the web page, will they be sent in a single TCP session or multiple TCP sessions? I'll do a poll, or you can answer in either chat. A single TCP session or many? I put it in the in-class channel, because that's the channel I was tabbed into. Okay, so most people said multiple, which is a good assumption to make, right? So good instinct to say that it's multiple, because if it was multiple, that would obviously be better from different efficiency points of view. If you think about it, obviously being able to download it over multiple streams is probably the superior option. Let's see. So, by default, you get a single session, and that's called a persistent HTTP connection, which is kind of a weird nomenclature for it, because it really doesn't have that much to do with persistence. It's not like it stops and starts or anything. It's just the fact that it's a single session that's used for all of the data, so that's why we call it persistent, but it's probably not the best word to use. Or, and this is the more commonly used approach by most browsers and servers today, is to prefer multiple TCP sessions, and generally they will try to do one for each file. This is called a non-persistent connection. But there are advantages to both approaches, so let's look at the advantages to a single or persistent session versus multiple or non-persistent TCP session. So first, an example of how non-persistent would work. So we connect to catforums.com via port 80. The socket is created at both ends. We do the TCP handshake. Remember, that has to happen first since we're doing TCP. And then client C sends an HTTP request to catforums.com for the index.html file. That's the first thing that happens, is the request for index. The server responds with index. That session is closed and the sockets are closed. Client C reads index.html and sees that there are 5 images in that file. And now client C repeats those steps for file 1, file 2, etc., etc. So it has to establish a new socket, do a handshake, exchange data, then close the socket. a bit of work to do. What are the benefits to this approach? What is the benefit? Well, the biggest benefit is parallelism. You have the ability to download multiple files at the same time. You can do Cat 1, Cat 2, Cat 3, Cat 4, all in different sessions. You could do Cat 1 and Cat 2 in 2 different TCP sessions, and then the other 3 in 1. Do any variation on those things. So browsers will typically run, the modern browsers, so your Chrome, your Firefox, whatever, they will typically run somewhere between 5 and 10 TCP connections in parallel. You can typically change the number of connections that run in parallel in your settings, and it depends on the version and what they've changed and how internet is in terms of its speed. As internet gets faster, you can run more in parallel, I guess. But why don't they run more than 5 to 10? Why is 5 to 10 kind of the limit? Why don't they let you run 100 in parallel, download 100 images in parallel? So think about that and answer in either chat if you have an idea. Why do you only run 5 to 10 in parallel in typical usage? Why don't you just run as many as you can? One for each resource. So why 5 to 10? Why not many, many more? We'll go back to that. What is your delay to getting data in this example? Somebody answered, you don't want your browser hogging all the ports on your machine, so they would all be over port 80. Remember, TCP allows you to make different sockets by changing the inbound port. All 4 things have to match: the source IP, the destination IP, the destination port, which is always 80, and then the source port, which changes for each of those TCP requests. So you wouldn't use up any ports. You would use up a lot of your sockets on your machine. That's not necessarily the reason why. We have a lot of sockets to spare. We could easily spare 100. The reason has to do more with performance. So why might we only use 5 to 10 instead of, let's say, 100? So how long until the client gets to read the first byte of index.html? And then I'm still soliciting answers for why 5 to 10 and not tons. And again, it's not always 5 to 10. It could be 20, whatever. You can go into your settings even and change it. But there is a performance reason why more than that is not necessarily beneficial. Someone asked if that presents a major amount of bandwidth for being used just by communicating with the server. Generally, we want to use as much of our bandwidth as we can. We want to talk to the server as fast as we can. And the server wants to send you things as fast as you can, because the speed at which the website loads is a big factor to the customer actually enjoying it. So customers want their website to load as fast as possible. Someone asked, is it due to overhead from the handshakes? That is part of it. Every time we open a new session, we have to do a new TCP handshake. That's a bit of delay and a bit of overhead. So part of it is the overhead from the handshakes becomes too burdensome once we have too many. Someone else said 5 to 10 can do the work fast enough that 100 would not look different to a human eye. It's actually even more than that. It's that 5 to 10 can do the work as fast as 100, really, for performance concerns. Why might that be? Why might 5 to 10 non-persistent connections basically be as fast as 100 from a performance point of view? So why is it that even though you have, let's say, 100 different images to download, you can download them over somewhere between 5 and 10 non-persistent connections just as fast as if you had made 100 connections, or roughly the same speed as if you had made 100 connections. And part of it was already answered. It was that overhead from those TCP handshakes. You're doing 50 times or 20 times more overhead if you have 100 versus 5. So you are already cutting into your performance a little bit there just by having all those handshake overheads. But then, all right, let's say you have all 100 established, how is it that 100 simultaneous TCP sockets, so basically 100 simultaneous threads, as we know from our development experience, each of those is probably going to be in its own thread. How is it that 100 threads is no faster than 5 to 10? What are the bottlenecks that are singled, basically, that make it so that multiple simultaneous sessions are not much of an improvement? Wait another minute for answers. Someone said there are not enough cores for all the threads to be working at once. That is part of it. Even on modern machines, most people are limited to somewhere between 4 and 8 threads running simultaneously before the practical advantage to more is relatively small. If you have a very nice modern computer, Ryzen or something, you might have 1632 threads to play with, so you are able to support a lot more simultaneous connections. But otherwise, yes, there's definitely a drop-off in the advantage to having multiple threads at a certain point. It doesn't matter whether you have 10 or 100, and you actually start to see a performance degradation from having too many because you have to switch between those threads, and that has an expense, and there's an overhead with creating them too. Someone said maybe if the threads have to share resources, it could cause issues. It could be, but you could probably figure out a way not to. Figuring out a way not to would probably incur some overhead. All right, the biggest answer, the most, I guess, correct answer is that the bottleneck is at your network connection or your network card. You only have one of those, right? And all of the traffic goes into the same buffer on your end and comes out of the same buffer on the server's end. So since you only have one network card and everything goes into the same buffer, there's a limit to how much you can receive in one time unit anyway. And the goal of creating a bunch of non-persistent sessions is to maximize the amount that you are getting so that your buffer is always full or your connection is always saturated. You're getting as much as you can. Typically, you can do that with 5 or 10 persistent connections, and once you've made more, you're not really saturating the buffer any further. You're just wasting more overhead on those TCP handshakes and, again, making new threads and all of this other stuff that just adds overhead. The 5 to 10 is usually somewhere around the sweet spot to saturate your network interface, which, again, you only have one of. You only receive a single stream of bytes coming in, and you only have a single stream of bytes coming out of your network interface card. So the advantage of having multiple different abstractions, multiple different streams in the operating system, although we think of it as multiple different streams, at the end of the day, everything is coming in as a single stream of bytes for all the different applications on our system and all the different resources that we're trying to fetch. So we do have to keep that in mind, that we really just have one stream of bytes in and one stream of bytes out at any given moment. And it's just the NIC that's doing all the work of sorting those and getting them where they need to be. And splitting things up into parallel sessions doesn't typically give us too much of an advantage there. Now, why do we use 5 to 10 instead of just 1? Because just 1 is usually not enough to saturate the connection. Stuff's not coming in fast enough. There's too much of a delay between a TCP segment's payload coming in and then we have to acknowledge it and all of that stuff. Whereas if you have multiple, then you're constantly getting data and acknowledging different data. So that usually is enough to fill it up. Now on the server's end too, server-grade NICs are more complicated. they can definitely do different things in terms of sending multiple packets at a time from different addresses and all this other magic that server-grade NICs can do. We won't get into that, but it's a little bit different on their end. So basically, the main answer, the most correct answer, is just that your network resources are the limited part, and there's no advantage to having a bunch of parallel connections when you only have a single network interface that can only take one stream of bytes at a time. The advantage of parallelizing starts to dip down after like single-digit parallel connections. So keep that in mind when you design your applications too, on the client's end, they should generally just have 1, 2, 3, 4, 5 threads open for their different network traffic at the most. The server, of course, has to open tons and tons of threads to service a bunch of different clients already. So from the server's point of view, it's also good not to have more than 1, 2, 3, 4, 5-ish threads per client, just so you don't get into thread overload on the server's end, where it has thousands and thousands open to service just a few dozen clients. So that's another important reason too. You don't want to overwhelm your server. Alright, so how long until the client gets to read the first byte of index.html when they make an HTTP request? It's quite some time, right? Because you have to get through the handshake. So at least in terms of round trip time, how long does the client have to wait until they can read the very first byte of index.html? How long does the client have to wait until they can read the very first byte of index.html? Assume that there is a request and reply type functionality in HTTP. That's a fair assumption to make, right? Yeah, someone said not very long. Yes, in absolute terms, it's all in milliseconds, so it really doesn't matter. But no, it is. All delays matter when they add up over time, and people are very sensitive about their different delays. So if you had a longer internet connection, something like satellite or something, and your ping was 250 milliseconds, the difference between 1 round trip time and 2 round trip time is a quarter of a second, very noticeable indeed. So someone said for RTT, you've got your client SYN, your server SYN-ACK, client ACK, and then server first payload segment. So RTT is there and back. So the client SYN and then the server SYN-ACK would be 1 RTT. The client ACK and then the server first payload would be 2 RTT. Let's see if that's accurate later on where we're going to think about it. Okay, so how long from the link being clicked until we get to read the first byte of HTML? So we know we burn that 1 RTT to establish the TCP handshake. So for the SYN and for the SYN-ACK, that's 1 round trip. And then it takes another half a round trip time, so just one way, not the back, for the client to send the HTTP request for that index.html file, and then another half a round trip time for the server to respond with that actual file. And this assumes that the client is putting the HTTP request in that final acknowledgement of the handshake, where remember we are allowed to put payload. And this is typically how you will see it if you observe it in Wireshark. You will see that the HTTP request comes out in that ACK, which is good because it saves us having to wait a little bit longer and maybe incur some more delay. So basically, the answer in chat was right, just multiplied by 2. It's 2 round trip time, and then plus however long it takes you to transmit index.html before you can even start rendering the website. So because we are over TCP and then HTTP is another platform where we need to send requests and get replies, there's a pretty significant delay before we even start getting our resources. So 2 round trip time to get the very first byte, and then however long it takes to actually receive it in order to actually get index.html and start to process it. Alright, so what's the advantage to a persistent connection over a non-persistent one? So we've seen that the overhead to headers and the TCP handshake is pretty substantial. So the advantage to persistence is that we don't need to wait an extra 1 round trip time for the handshake for each connection. Remember, the TCP socket gets closed at the end of a non-persistent session, and then they open a new one to access the next resource. Opening a new one incurs that TCP handshake, whereas not doing that means that we can just send a new HTTP request, and we don't have to incur that handshake and the subsequent delay. Let's skip a slide now. So there's an advantage to both, and a mixture of both is really where the sweet spot is. A mixture between persistence and non-persistence is definitely the sweet spot. Let's look at a few of the different HTTP request types that there are. There really are not that many, and actually most of them aren't used anymore. You really just have GET and POST. That's pretty much it. The whole internet runs essentially on GET and POST. So you've got GET, POST, head, put, and delete are the main ones. GET is simply to request a specified file at some URL. You will see this nomenclature in other different applications that request files. Like on Linux, you will see wget, webget, basically the same syntax. So get is the commonly used word to refer to fetching some file from a server. That's sort of was established, and now everybody typically refers to it that way. So if somebody's telling you a GET request or a GET is happening, that means that a client is requesting some file from some other client or some server out there on the internet. And then the other way for the client to be able to send some information back is the POST. A POST lets you send some text back to the server. Now, what's used today typically, because POST has some problems, is that sometimes clients will actually send their data back using a GET request, and they will bake the data that they want to send back into the URL. And so the server is configured to handle it that way. This is maybe the more common way to do it today. So you would go to website.com/submitmyform/username, or get/username/password, etc. All of that would be in the URL itself instead of in a POST request, and then the server would process it that way. The advantage to POST over GET is that POST doesn't show up in the URL bar, but as you know from browsing the internet and seeing all the crazy long URLs that you get at the top, most websites are probably using GETs then, because GETs do show up in your URL bar at the top of the screen there in your browser, and so you are seeing basically the changes to the URL. Those are changes to those GET requests. When you submit a form, when you log in or something, you'll typically see the URL change to something like www.website.com/login, ? And then a bunch of gobbledygook. That's probably your encrypted data being sent back to the server or what have you. There's also put and delete that were used to upload and delete files from web servers back in the day when people used to administer their own web servers and they didn't have fancy tools like IIS and everything, and those are almost never used today and typically disabled because of the security concern that they cause, that if somebody is able to get access to your web server, they can upload and delete files and all that stuff, and just generally speaking, they're not that useful because there's better ways to do it. You've got your response messages. These are the messages that the server sends back to the client in response to a request. So let's say that the client sends a request. Here are the different things that the server could respond with. It could respond with message code 200, which means okay, everything's good. It could respond with 301, this resource has moved. It could respond with 400, bad request. It could respond with the infamous 404, I did not find that file. So 404 means that the resource that you were requesting, the resource you attempted to get, does not exist at the URL that you specified on the server. So it's not in the folder on the server where you said it was or where you asked for it to be. Or the 505 HTTP version not supported, because HTTP has gone through a few versions over the years. It's possible that you have a mismatch. Basically, all of these but 200 and 404 are very rare. Occasionally, you'll see 301, but I mean, very rarely in typical browsing. You'll very rarely see 400 unless there's something wrong with your connection and your packets are being corrupted or something. Typically, you'll just see 404s, if any of these messages, and obviously the OKs. So we'll save this for next time, but we can do a little bit of HTTP over Telnet. But yeah, we'll do that next time. So that's HTTP essentially. We'll look at it a little bit more next time, and something to think about as you design your own applications. If there are no further questions on this or the homework. We're going to call it a day, and hopefully those of you who couldn't join us today get your power and internet and etc. back soon. I know mine is running, but there is a giant tree leaning on top of the power line, so it's like, okay, it could go any minute. I'm glad it didn't go in the last 50. And if I'm not there for office hours, it's because I'm in a blackout. So I will see you guys next time. Thanks for tuning in.